Ciurlo from UCLA. Anna did her undergraduate and master's work in Genoa, Italy, and then got her PhD in 2015 from the University of Sorbonne in Paris, and was a researcher there at Paris Observatory for a year, and then a visiting scholar at Keck Observatory for a year. Was a postdoc, and now is an assistant researcher at University of California, Los Angeles. So she's in the black hole, the Milky Way black hole group, which of course rocketed to international attention in 2020 when Andrea Getz shared the Nobel Prize. So that's a group famed for hard work in regions of adaptive optics, infrared observations, and pursuit of all the issues related to black holes of the Milky Way, including detections, tracking the stars, general relativity, the whole thing. There was a paper maybe 2 years ago that was just nice, thick, just seminal paper on the work they've been doing. But we're going to talk more. Anna's going to talk more about the interstellar medium near the black hole, I think. And here we go. So thank you so much for joining us, and we will shout out questions for clarification, but we'll save most of our questions for the end.
Great. Thank you. Thank you very much for the introduction and for the invite. So as you were saying, I am in the Galactic Center group, but I'm doing kind of a complementary side to the stars. So I'm going to talk mostly about interstellar medium, but also about its connection with the black hole and the stars and so on. So it all fits in the same picture. So here is a short outline of the talk. Let me start with the brief introduction. When we talk about Galactic Center, that means different things to different people, because it can be a lot of different scales. Generally, people, when they say Galactic Center, they mean the central few hundreds of parsecs, but it can go much below the 100 parsec scale, even to the sub-parsec scale. So there are multiple scales of gas and stellar structures, and in the very center, there is the black hole, named Sagittarius A star, a 4 million solar masses black hole, currently not very active. Is not currently very active, but we have evidence that it was more active in the past. For example, at very large scales in our galaxy, we see the Fermi bubbles. They might be related to the release of a vast amount of energy emitted from Ciurlo star. And we do see in other galaxies that the supermassive black hole at the center can ingest large amount of matter, and then that can power high energy jets. This kind of phase, if that happened in the past of our own black hole, can be responsible for producing features such as the Fermi bubbles. If we zoom in, from the galactic scale to the hundreds of parsecs, this is what's called the central molecular zone. It's an area filled with massive molecular clouds, and this is most likely the endpoint of a chain of matter inflow that comes from dust lanes that come from the higher distance galactic bar. So at the parsec scale now, zooming on even more, I'm zooming very fast, like by order of magnitudes, we find a huge amount of stars, the nuclear star cluster. This can prove star formation nearby a supermassive black hole, so it's interesting for many reasons. In the central cubic parsec, there are 1 million stars, whereas in the same volume in the neighborhood of the solar system, there is just one star, the sun. So it's a very crowded environment. Most of the stars are old red giants, but most of the radiation comes from young stars like OB or Wolf-Rayet stars. If you zoom in even more, there is a strong cutoff in the density profile of the stars at around 0.04 parsecs from Ciurlo star. This defines also a distinction between the type of stars that we see. We see more B stars at these smaller radii, and we find a cluster of randomly oriented orbits within 0.04 parsecs of the black hole. This is what's called the S stars population. S stars doesn't stand for the type of star, it's just S stands for star. So it's the star-star cluster, the S star cluster. And these are the stars that have been used to prove the existence of the supermassive black hole. That's what was referred to before the beginning of the talk. The Nobel Prize in Physics was in partly given to Andrea Ghez because using the motion of the stars that we can track in this region, we could prove the existence of object that basically could only be a supermassive black hole. So the galactic center is interesting for many different reasons. There are different types of physics you can do, and there is a very important interplay between scales and components. And each is important to put together the jigsaw puzzle that is this complex region. So we look at the galactic center through the lens of understanding the mechanism that regulates galactic activity. We just have one sample, the only galaxy we can see so closely. So we have very high resolution, but just one data point. So what does it mean galactic center for me? In my case, I concentrate to the parsec to sub-parsec scale. So for this talk, I'll be focusing on two different scales, the parsec scale and the 100th scale. So let's start with the first one. Here we can trace molecular gas, and basically we look at the reservoir of matter that could eventually fuel the higher activity phase for the supermassive black hole that is currently quiet, but it was not that quiet in the past and might get more active in the future as well. So I showed the field of stars here with the different stellar structures, but now we can look at the same field and look at the interstellar medium instead. So we see primarily at the scales two structures, the circumnuclear disk or CND, a ring of dust and molecular gas. It's believed to be fueled by infalling dense clouds that come from about 10 parsecs away, and it believed also to be able to release material into the central cavity. So even though these features have been known for a while, there are still a lot of uncertainties of its physical state, which makes it unclear if it's structures that is stable and whether the conditions are right for fitting the next generation of star formation in the center of the galaxy. The second structure, yes, and this is rotating. These are just two figures to show you the larger scale structure. And we know that there are all these massive stars and windy stars in the center, so they have the effect of ionizing the central cavity of this ring. And then we have the second structure, the mini spiral. These are basically strings of infalling ionized gas and dust. And the proximity of the CND, the mini spiral, means that they are intimately related to the activity of the nuclear star cluster and of the supermassive black hole. How exactly is not clear yet. That was this is just a plot of the dynamics of the mini spiral. It looks like a spiral just when projected in the plane of the sky, but it's actually made of these arms that come from different directions and are related somewhat to the nuclear disk. But except for this ionized gas, we also see some molecular hydrogen in the cavity of the circumnuclear disk of unknown origin. Okay, so this region is very rich. I'm sure you're convinced of that by now. It's a complex region where there are multiple phases and components. And so in order to characterize the emission at different scales and characterize the physical state, understanding the interplay between the components, we need a lot of information because we need to characterize lots of different components. And for this region, integral field spectroscopy is a great tool to use because it's something that helps disentangle components. Because with the integral field spectroscopy, you obtain a data cube where you have two spatial dimensions and one wavelength dimension. So even though you have multiple components superimposed on the line of sight, you can disentangle them because they have different Doppler shift velocities with respect to the observer. But this type of data is complex, especially in such a rich region where there are so many components. So sometimes it's still hard to disentangle them. So we have been using an innovative technique called CubeFit. They basically inject a priori information on the gradient of your emission, and it's so very well suited to study extended features, for example, the clouds of the circumnuclear disk or of the mini spiral. And in this way, you can extract even low signal to noise emission because you take into account the fact that neighboring pixels on your data cube are actually correlated. This is an example. If you do fitting of your data cube pixel by pixel and you look at the line emission and you look at the width of that line emission, it can get kind of noisy results even if you smooth it. But if you use CubeFit, you get a map that actually is able to recover much more of the intrinsic structure of the emission. So it's quite powerful. We have applied it to a variety of data in the center of the galaxy. We used it on VLT data in the H and K band, and we were able to find that there is emission coming from molecular hydrogen all over this region. In the central parsec, we are mostly probing the center of the circumnuclear disk. There is a little bit of emission that is associated with the circumnuclear disk here on the sides, but there is still a lot of H2 emission inside the cavity itself, which is surprising because, as I mentioned before, this is very ionized, so you're expected to dissociate completely the molecular hydrogen. So where does this come from? We have also applied it to the circumnuclear disk itself, and we do see that there is molecular hydrogen in the clouds of the CND where it's expected to be, and there is basically a layer of ionized gas on top of it. So how comes that you can also see molecular hydrogen inside the rim of this disk? Well, it's not clear yet. Let me just jump to this. We don't see any large scale motion that could explain why you get this gas into the cavity. Could be because an easy explanation would be this just migrated inward from the CND, but we don't see a large scale motion of the gas. Another possibility is that this is actually formed in situ, and it is a very unionized environment. But if you have windy stars and you're far enough from the star, maybe you can have enough dust grains that are not hot, not too hot, where you can have H2 formation. So they could be forming around the Wolf-Rayet stars that are in the regions, for example. But this is kind of an ongoing investigation. We can also apply CubeFit to larger scale, and this is a figure from KMOS at the VLT. At this scale, you don't have the same resolution as the other data, but it's interesting because you can investigate the interplay and the relationship between the circumnuclear disk and the mini spiral, having this very rich type of data. Concerning the molecular hydrogen, not only we find an emission inside this region that is very ionized, but also this emission is peculiar in many ways. There is very strong deviation of the local thermal equilibrium in one spot that corresponds to the location where the three arms of the mini spiral are colliding. So there might be some interesting type of excitation that are not quite explained by the current models we have for a molecular hydrogen excitation. And this is a plot showing you exactly that. If you use models that you see here on the bottom and you compare them to the observations, it's very hard to reproduce both the type of intensities that we see and the shape of what this is called the excitation diagram. So the column density as a function of the energy of the upper level of your molecular hydrogen transition. Okay, so you have lots of interesting structures at this scale, and one of the reasons why we want to figure this out is because we don't know if the CND can be the reservoir that can fuel star formation, how stable it is it a transitory feature, or is it gonna reach the black hole, form stars, and power a new phase of very increased activity? We know from other galaxies that there is much higher activity that we can observe nearby black holes of the same size as ours. So ours is kind of quiet given its mass. But we are also lucky not to have a black hole that is too active, because this way we can really peek through the veil and see what is in the center and look at those stars. And for example, we were able to prove the existence of the black hole that way. But for now, since the activity is not great, we can imagine that CND would enhance the activity later on. But we also know that there are more phenomena that can increase the activity of the black hole. We're talking about much lower scales. So we see the black hole having spikes in activity from time to time. And since we can look so close to the black hole, we can try to track what produces this type of smaller scale activities that the black hole produces on a much more regular time scale. So to look into that part, let's focus on a much smaller scale than 100 parsec scale. There are many things I want to talk about, but let's start with just a picture where we are looking at. This is the same image we were looking at before. We see the stars with the nuclear star cluster and so on. We were looking at the central parsec, but here we are zooming even more. So this is a zoom in of the central parsec, and we're looking at the central few arc seconds, so 0.04 parsecs, for example. This is at the scale at which you see all these S stars orbiting around the black hole, and these are the stars, especially this in particular, this star S2, or also called SO2, which was used to probe the existence of the black hole over 20 years ago. So let's look at the zoom in. This is a rendering of the orbits of the S stars. And the star I was talking about, SO2, is over here. This is the one that allowed the discovery of the black hole, but also we have been observing this region long enough that we have seen SO2 actually complete more than one full orbit. It takes about 16 years to complete one orbit. And this was used now 4 years ago to prove general relativity in nearby supermassive black hole, because SO2 passed so close to the black hole that we could measure the gravitational redshift that is due to the presence of the black hole itself. So the S-stars are great, very interesting. You can prove there is a supermassive black hole there. You can test the general relativity. Now the next step is also testing general relativity and beyond. Since we have observed more than one full orbit for SO2, we can start seeing there is a precession of the orbit that could be also due to gravitational effects. But not only stars orbit the supermassive black hole, there are other objects as well. In particular, G1 and especially G2 have been drawn a lot of attentions in the last few years. So what are these? They appear as dust and gas emissions, so they look like blob of gas and dust. They are unresolved and most likely quite large, like a few hundred AU, and they can come quite close to the supermassive black hole, 100 to 1,000 AU. So G2 in particular was very interesting because it was discovered only 2 years before it was expected to reach its closest point to the black hole, its closest approach. And since this appeared just a blob of gas and dust, people expected it would be completely destroyed by the close encounter with the black hole. And people got very excited because they thought that that could potentially trigger accretion. And so we should see an increase in the activity of the black hole in real time. So the closest approach for G2 happened around 2014, but it turns out G2 survived, and the crazy activity everyone was expected to observe didn't materialize either. So what are G1 and G2? It's not clear, but we know that they are not alone. We have a lot of data that have been collected to monitor the galactic center. This is data that's been collected to monitor the S-stars, but this includes both imaging data and imaging spectroscopy data. And this imaging spectroscopy data in particular is extremely rich because you can not only see the stars, but you can also see the interstellar medium. So what I did is look at, well, now it's not 13, it's like more like 18 years of data where we can observe these data cubes and see how the interstellar medium evolves. And since, again, these are complex data sets, data cubes, right, with the 2 spatial dimensions and 1 wavelength dimension, in order to disentangle the components, I use this 3-dimensional visualization tool called Ostrosval that allows you to visualize your cube in 3 dimensions and turn it around. So I take my cube, I want to look at the emission gas, so I'm focusing on the hydrogen emission combination line bracket gamma. So I cut it around this emission line. I remove the continuum, otherwise you only basically see the continuum of the stars. Here is your cube, and then with this tool, it's actually a lot of fun. You can turn it around and see which kind of components can you disentangle on the line of sight and in radial velocity for the bracket gamma component. So doing that, we identified several compact objects, compact sources that have many of the similar properties as G1 and G2. So we see them here. We call them G3, 4, 5, and 6. Again, this is a view of the data cube from the side. So this is the spectral dimension. So what's interesting is that we do this game year by year, so we can slice our cube and look at the proper motion evolution of these objects. For example, you see here G3, 4, and 5. And you see here G5, just because I cut the cube in the blue shifted region and in the red shifted region, you can see it here. But then you can also cut your cube along the spectral dimension and so extract a spectrum and see how the radial velocity of these objects evolve. So combining these two, we get orbits the same way we do for stars. And so the result is that we have these 4 additional objects that behave in very similar ways as G1 and G2. They all lie within the central 0.04 arc seconds from the black hole, and they also have orbits that are on the orbital parameters scattered all over the place, which kind of resembles what the S-stars population show. These are on similar spatial scales as well, so it might be that these 2 populations are actually related somehow. So, but how it comes that these blobs of gas kind of look and behave like stars? Because they have similar orbital properties. And in the case of G2, for example, they survived the closest encounter with the black hole. So maybe this is not just made of gas and dust. So what are the different possibilities for the origin of these objects? Here are a few scenarios. So the first idea is that these are just gas clouds. That's what the very first observation suggested, because that's the emission we do see. But there have been, since the discovery of G2, many suggestions that raise the possibility that there is actually a star, probably a not very massive star, that is hidden inside these objects. So a star surrounded by dust and gas would have an emission that we cannot detect with the instrument and the sensibility we have right now, but it's there and it's keeping the object kind of together. So, but how do you get this star surrounded by gas and dust? There are many different possibilities. People have suggested protoplanetary disk disrupted, maybe by the gravity of the black hole and of the many stars in nuclear star cluster, or a star that is losing mass, or a merger product. Merger product is quite interesting because it's what's called, it's a byproduct of the eccentric Kosalidov effect, which is an effect that say that binaries in the neighborhood of a solar system have a tendency to merge more often because of perturbations due to the presence of the black hole itself. And we do know that in general, in a stellar population, there are many binaries. And if you have many binaries also near a black hole, you would expect them to merge, and you can observe later on their products as a G object. So let's focus on the different pros and cons of these different scenarios. For the gas clouds, it's kind of a very simple explanation that fits what we have observed so far. But the problem is that G2 is closer encounters. So how can you do that without a massive objects that actually keeps the source together against the tidal disruption? Protoplanetary disk is also a good explanation because they are objects we observe elsewhere. So they might exist also in the center of the galaxy, but it turns out that in order to have this to actually look like a G object, simulations show that you need conditions that are just right. So it might be difficult to produce multiple events that show all these conditions to closely match your observations. So what about a star that is losing mass? This is also produces an object that is compact, but kind of puffy with all this gas and dust around. It's something that is also easy to produce, but it's not a mechanism that is specific to the center of the galaxy. So we would need to observe something that looks similar to that also elsewhere in the galaxy. And the merger product has the pros that is a mechanism that could be really specific to the center of the galaxy because it depends on the presence of the black hole itself. And it's something that is actually expected of models like that apply the eccentric Kosalidov effect to our galactic center. But of course, you need to have binaries in the galactic center. It's not clear if the same binary ratio observed elsewhere in the galaxy also applies to the center of the galaxy. And we don't have a very clear idea of how a merger product would evolve. This imply very complex hydrodynamical simulations that we don't have at the moment. But I think what comes out of this is that we expect this to most likely have a stellar object hidden inside. So the most likely scenario is that the G objects are bloated up, dust enshrouded stars. So you have a star, probably not very massive, maybe 1 or 2 or 3 times the mass of the sun, surrounded by dust that is heated by the central source. And on top of that dust, a shell of gas that is ionized by the surrounding stars in the center of the galaxy. So this is what is shown here. The star is hidden inside, then we have the dust rendered in red and the gas around it in blue. So, but again, why are they like this? Why do they appear so puffy and dusty? And among the different scenarios that include the star, the one I like the best is the binary merger product because it fits well in many ways. We know, for example, from models that most of the binaries that get formed in an event kind of emerge early within a few million years. And we know that the latest star formation event in the center of the galaxy most likely took place about 6 million years ago. And we expect the dusty phase after the merger happens to last a long time. So it kind of makes sense with the timing that we had binaries in the latest star formation event. Most of them have merged and some of them are still visible today as G objects. Another possibility is that this is connected with the stars population. As I was showing before, they are on a similar spatial scale and they show similar orbital parameters. so maybe in earlier star formation events, if you think about star formation as an episodic series of events in the center of the galaxy, if you have your binaries, you merge them early, but then at some point this dusty phase has to end. And when the dust is gone, it has been shown that when you merge two stars, you can produce a new star that looks younger. This is what we observe in some local stars. And this could be something that helps explain why you can observe young stars near a supermassive black hole, which is quite surprising because we would have expect the tidal forces of the black hole to prevent molecular clouds collapse and the formation of stars so close to a black hole. So this is what is called the paradox of youth. It's you would expect only to observe older stars in the center of the galaxy that got formed elsewhere at larger radii and then migrated inward. But you actually observe stars that are too young to have migrated from the outskirts of this region. And this is not completely solved, but one way of connecting to this is that you could rejuvenate stars through this merger mechanism. It's just an hypothesis. It's not clear how much you can actually rejuvenate a star and if that's enough to match the ages we see, but it's an interesting possibility nonetheless. One important thing is trying to figure out this question is, well, if it's the black hole itself that creates the G objects because it's making binaries merge more often because they're close to the black hole, then we would expect to see a radial dependence on the number of objects we see. Well, of course, just to underline the fact we only have a sample of 6 objects so far, but we have been observing also a region that is quite small. We should now probe larger radii, and we have some data that can help us. We have some candidates. So you can see here some candidates from different publications. These are dusty objects that we need to track and see if they resemble the objects we know so far. But simulations kind of indicate that we would expect the number of objects to decrease as a function of radius. So basically, we wouldn't expect many objects outside of this solid line. And this is work in process, but it's something that can help us figure out what the G objects are. Just to give you an overview of the different scenarios for the G objects, we have several of them. So this means that you need a common formation mechanism. And there are many scenarios that I've presented. This could be a cloud, a merger, and the envelope from a mass-losing star or disrupted disk. But each one of these scenarios can tell you something that is very interesting, not just because you want to figure out what these mysterious objects are, but if this is a cloud, you can track tidal interactions and accretion on the black hole. You can kind of do that as well in the other cases, but even more if it's just a pure gas cloud. In the case of a merger, well, you can actually track the supermassive black hole effect on stellar evolution and how that changes because of being close to a black hole. And in the case of envelopes from mass-losing star to disrupted disk, you can maybe track if there is any ongoing star formation near a supermassive black hole, which is a question that is a contested one and is the subject of very active discussions at the moment. Some people say they see young stellar objects, some others say they don't. And it's kind of an open question whether there is any ongoing star formation at the moment, which fits into this youth paradox of how you can have young stars so close to a supermassive black hole. So in this context, I want to talk about a very different objects. It's called X7. You might have seen it in one of the earlier slides when I was showing this cutouts. You can see it up here, peeking in, but let's focus on it for a second on this. So this is something that looks very different from the other G objects. Is very extended, and I showed you the evolution of the G objects. They are mostly unresolved or very marginally resolved. This one is resolved at least in one of the dimensions, and we have observing it for the last about 20-25 years, and we have been seeing it having this dramatic evolution. It's getting stretched more and more. Maybe there is some tidal shearing that is happening and is really changing in shape and in length. So to me, this is what a gas cloud, a pure, true gas cloud actually do when you look at what happens when you're in a supermassive black hole. And we know this object is not associated with a star. We don't see any star that moves together with it. So it could be that it's something hidden inside as for the G objects. But as far as the stars that we know, we don't see anyone that is associated with it. We know its orientation is not aligned with magnetic field lines, given the model we have right now that have limitations, but doesn't seem to be aligned with with it, or with the stellar winds coming from the Wolf-Rayet stars in the regions, or a possible Sagittarius A jet that has been suggested in the region either. So this is a shape that is completely on its own. It's not clear where it comes from. So how did it form? Well, it could be, for example, the result of a collision between a compact object and a red giant. There are simulations that show that that can produce something that is similar to X7. It could be connected to G3. We know that they have very similar orbits, so maybe the stellar merger that produced the G3 also ejected some gas in the form of X7. This is still under investigation. Or maybe X7 was stripped from larger scale gas, such as the northern arm of the mini spiral, even though its orbit is really different. So you will have to figure out how you can remove so much angular momentum and put it on this kind of very tight orbit. The tidal evolution of X7 can be completely explained by the gravity of the black hole alone. We did that with this toy model, kind of pearls on a string. And if you just consider them each one independently and see how, given an initial position and a radial velocity gradient along X7, you just let it evolve with the gravity of the black hole, then you can reproduce exactly the type of behavior we do observe with X7, this stretching and lengthening, keeping this constant angle on the plane of the sky, and also the radial velocity distribution and evolution as well. So it seems like the most important component of how this object evolves is the gravity of the black hole. But you need to give it this injection of initial radial velocity that we are not sure where it comes from, maybe a collision, maybe a merger product, and so forth. It's interesting because we don't know exactly what kind of mechanism produced this, but also, again, this can show how you can have tidal interactions near a black hole. And we have some data that showed that it seems to be detaching part of it. We expect it to eventually be completely destroyed in the next 10 to 20 years as it comes closer to the black hole. So since it's expected to break up, is it gonna trigger any accretion? This is the same question we have for all the G objects. G2 was expected to trigger accretion and so enhance activity. Maybe X7 will in the future as well. Also, the star SO2 passed very close to the black hole. So did actually any of these produce an enhancement in the activity? Well, that's a very hard question to answer. We did observe a very high increase in the activity of the black hole in 2019. This is an animation showing you images within an hour of the supermassive black hole. So this star here, this is SO2. This is the brightest star closest to the black hole, the one that has been used to probe the general activity around it. And here you see the black hole, well, the material around the black hole emitting and coming in. Usually you don't even see it. Usually this is the state at which we see Surgery star, and then it comes up very, very bright. You see this spike in luminosity. So this happened 1 year after the passage of SO2 and 4 years after the passage of G2 and the closest to the black hole. So either of these objects could have contributed to this enhancement of the activity, or maybe some other objects that we have not detected, closer in stars with smaller periods that we have not been able to detect yet because they're confused or they are very faint. To figure out if any of the known objects actually have contributed to this a very high increase in the activity, you have to model very well your accretion flow, which we don't know very well. Speaking of which, the accretion flow in general, especially when it comes from warm gas, is very poorly constrained. We know a lot from X-rays, but not that much from the other gas. A few years back, there was a claim of detection of the accretion disk of the CJ star from a line, an hydrogen recombination line observed in the radio. These authors observed this double peak emission, very broad, with the blue shifted and the red shifted peak that seems to reproduce what you would observe. You observe an almost edge-on disk with this blue shifted and red shifted sides. So we looked in our data because since we have so much data in the near infrared, we can look and compare this line to the Bragg gamma recombination line, which comes from a much lower energy transition, Bragg gamma. And we combined 15 years of data, so we got a very deep spectrum of the same region. That's the one in orange. And the only gas we see is the one that you see here, this very narrow emission. This is just foreground gas we see all over the region. We don't see anything that is as broad as this one or as intense, which is surprising because given that this transition comes from a lower energy level, you would have expected to have an even stronger emission in bracket gamma than in this line H30 alpha, but we don't. So what does it mean is not clear yet. Maybe there is some kind of amplification or some kind of peculiar excitation, or maybe this accretion disk is a temporary feature or something else. It's kind of interesting. But this non-detection in bracket gamma is important because it can give a very strong constraint, observational constraint on models of the accretion flow that we didn't have before. So I'm at the end of the talk. I kind of touched on a lot of different science, so I want just to show this family portrait of some of the fun science we can do with data in this region. So I'm highlighting different data sets. We talked about molecular hydrogen, where you can trace extreme conditions. You can compare the molecular gas in the cavity and in the CND. You can try to figure out where this H2 in extreme conditions is coming from, maybe from this the atmosphere of evolved of young stars. You can also look for intermediate mass black holes in this region. This is some other work I've been doing. And you can try to figure out the accretion flow, looking very close and very deep in the infrared as well. And this is all things we can do with the mostly KEC and VLT, but something fun that just happened, we just observed these two fields with JWST, with the MIRI-MRS, it's the integral field spectrograph in the mid-infrared. So stay tuned for more fun, interesting science on this interesting region. And this is just a quick summary. We have been observing the galactic center obsessively for a very long time, over 20 years, 25 years now. And you can look at different scales. You can look at the parsec scale gas, where you can look at the gas origin excitation, which is still unknown. And you can try to figure out if there is an inward flow and if the conditions are right to a fuel star formation events in the future. At the sub-parsec scale, there are many different objects that can tell you many different things. For example, this dust and rotted objects population. Is it a population of binary merger products? Does this bring material onto the black hole? The same thing, it's the same question you can ask it for this tidally stretched cloud X7. Is it going to accrete onto the black hole? How did it form? Is it connected to binary mergers and ejections of gas? Are any of these going to increase the activity of the black hole? Did they activity of the black hole increase because of the passage of G2? And what about the accretion at all? Is there an accretion disk or not? Is there any peculiar excitation and type of physics we are not quite figured out yet? And how can we better constrain the models? These are all questions you can ask looking at this type of data. And so in the future, we'll keep on monitoring this interesting region. And the idea is that as telescopes get more powerful, we might be able to do something similar also in other nearby galaxy, or maybe just look at similar environments to look for G objects and figure out molecular hydrogen conditions. It's very important to look at different components also in different wavelengths, radio, infrared, both mid and near infrared, and comparing to the X-rays is important to put all these pieces together. And ultimately, our goal is to understand this environment better, to track the effect of the supermassive black hole on its environment and vice versa. With that, I'm done, and I thank you very much for your attention.
Hey, fantastic. I have just a general question. So in the sort of either at the parsec level or the 100th parsec level, surely there's just a huge amount of material along this line of sight, stars and gas both. So kind of in general, how do you sort out all that material that you don't want? When observationally, how do you reject it?
Yeah, so there are multiple ways you can do that. Typically, when you see an emission, you can look at its Doppler shift velocity. If it's moving faster, you can expect it to be closer to the black hole. And the trick we have is that we have multiple years of observation. So you can see how things evolve year by year. And again, you expect things that are closer to the black hole to evolve more quickly. So you can see if it's just an emission coming from a clump of gas that is on the line of sight or not. And you can also look at the type of excitation. If you see something that is very excited, the type of excitation we saw with the molecular hydrogen, for example, this has to come from an extreme environment. So it's more likely to be in the center of the galaxy. So both your timeline, your radial velocities, and your excitation tell you if you have if you're closer or further away from the very center.
Mm-hmm. Michael wanted to know if there was some educational material easily accessible about the galactic center.
Specifically looking for data, because it'd be a fun data analysis problem to just like get those and see, can we estimate the mass of the black hole, etc.
So there are a few videos we have done in the group for outreach events. You can find them at our YouTube channels. If you look at UCLA Galactic Center Group, there are a few videos that explain the galaxy, the black hole itself, how do you get a black hole to be a black hole, right? How much mass you have to enclose in what kind of volume. There is a few videos that are on YouTube that might be what you look for. If there is anything specific, I mean, I'm always happy to.
I'm looking like for digitized data if in the images about where the stars are as a function of time. So then we can try and match those, fit those, etc. So a little bit, doing the image processing is a little complicated probably for a class, but if we had those tables of data, then I think we could try and do some fits for orbits and stuff.
Yeah, I mean, all the publications do have their data points, so the astrometry and the radial velocities of the stars. So even if you look at this 2018 paper, Doe et al. In Science, that should have all the data that have been used to measure the Doppler shift, then you don't need to probably do a general relativistic model, you can just do a Keplerian model. But this we always published our data points in our paper, so you can get the data points from there. Otherwise, you can check out our website as well, the UCLA Galactic Center Group. We have some videos there, or the YouTube. If there is a specific image you're looking for, feel free to email me and I can see if I can send it to you.
Okay, thanks. And is the data in the paper in machine readable format?
I think it is. If you connect to Science, I believe that's an ASCII file that should be able to be downloaded.
Thanks.
If not, just email me.
Sukhan?
Hi, interesting talk. I was wondering, do we know how fast this the central black hole is spinning, and if it is fast enough to maybe have relativistic effects on its neighbors?
Yeah, we don't. It's one of the things we would like to know. There have been some, I think, attempt of measuring it in some of the Event Horizon Telescope papers that have come out recently about Surgery Star and its reconstructed images, well, reconstructed videos of Surgery Star, but it's one of those parameters we cannot really prove with stars directly right now. But it's definitely an important parameter. It's just that with the measurements we have not been able to constrain it yet.
Okay, if I can slip in another quick one. The intermediate mass black hole hypothesized. If it is true, I mean, how far is it? It's somebody else's work, I realize, but do you know off the top of your head?
Yeah, no, I mean, there's this, this is about, in parsecs is probably 0. What is it? Maybe 5 arc seconds, roughly. So that's 0.5 parsecs maybe. So it's close. So I mean, we don't know on the line of sight, so that's tricky. But there has been a talk about an intermediate mass black hole sitting in what's called IRS-13 for a long time. People have been claiming that for a while. There are some observations in ALMA that also seems to show disk-like emissions that might be associated with accretion disks around it. We also saw that just modeling, because this is a cluster of wind stars as well. If you just model the interaction of the winds, that also kind of produce the same emission we observe. So it's not clear if there is one. It is a big question if there is an intermediate black hole in that region or not, but so far we have not seen very strong proof that there is one.
Okay, yeah, because and even if it is one, it seems like it's far enough not to be like detectable by the pulsar timing arrays in gravitational waves. And this would be at least several years orbit, not of the order of a year or so.
Yeah, probably.
Yeah. Okay, thank you.
Yeah.
I was doubling back to the spectroscopy. I was wondering, have you investigated beyond hydrogen for like spectroscopic analysis?
Yes, we know that the G object seems to have also some iron-3 associated with it. If you look at this map, so these objects are kind of at this scale, and we know that this region has strong iron-3 emission. I can show you maybe a quick plot. Here. So this is iron-3. And so you have iron-3 in this area. So it's not clear if these objects have it because it's kind of in the area and they kind of carry it with them, or it's just that it's just because of the ionization that is in this area, or is something that is specific at the object inside. I think it's most likely environmental. So we have been looking at different lines, but the wavelength we have so far is not extremely large. We have mostly around 2 microns. So that's why it's going to be interesting to see what GWST has to add to that.
I'd like to ask about the origin of the molecular hydrogen in the area.
Yep.
And so you've got hot stars that are emitting UV, so you'd expect that environment to be ionized. But the source, I think you mentioned in passing Wolf-Rayet stars, but then later on in the talk, we were talking about intermediate mass, sort of 3 solar mass objects that were useful for other things like making gas clouds.
Yeah.
So yeah, what are your thoughts on what is injecting, or what is, what's the ecology here? How does the supply of cold molecular hydrogen compete with the ionization from these hot stars?
Oh, just one quick note. When you look at molecular hydrogen emission lines, you can only track the hot gas, it's not the cold part. So usually what we do is, since molecular hydrogen, when it's cold, it doesn't emit very strongly. We use tracer molecules like CO, HCN, and so forth. And when you look at H2 lines, you're looking at, especially in the near infrared, only at the very hot gas. So that's why for the CND, we have this dense colder gas clouds, but then on the surface of those clouds, you have kind of a thin layer of H2 that emits because it's ionized by shocks or by the radiation coming from the hot stars. If just a clarification. Then in the central cavity, still, why would you have H2 there? Even if you produce it, that should be very short-lived. I mean, we have to do precise modeling in order to figure out exactly how short-lived, but we don't really see it kind of flowing into the cavity itself. So maybe it's produced in situ. That's what kind of prompted the question. And I was talking about Wolf-Rayet stars because if you have a star that is windy, you can have this layers that can be kind of far from the star. And if those layers have dust on top of them, maybe they're not too hot. And if you have dust that is about, not above, I think 400 Kelvin, you can still have molecular hydrogen forming into it. And this is just a map of dust temperature that we have been working with a student of mine. And it could be that you don't reach those very high temperatures. So you could have dust grains in the regions that are not too hot. So you could form it, then you destroy it. But maybe if you continuously form it on the outer layers of the atmosphere of these hot stars, then you can keep on seeing, and so you make enough that you can detect it. This is kind of the idea. It's not finalized, it's just an hypothesis. The few solar massive stars I was talking about, these were connected to the G objects population, so something different. In that case, the star, I suppose it's has a small mass because we don't see it, so it's probably below the detection limit. And I think we can detect stars now down to maybe 3 solar masses or 5. But if you also enshroud it in dust, maybe you can hide an even slightly higher mass star. But the idea in that case is that since we don't see continuum emission from the star, that's maybe because it's low mass. So it's two different arguments.
Thank you. That clarifies things for me. I don't know if it would help the audience that much, but I thank you for that explanation. That's good. Anything else here? I would like to remind this crowd that next week we are meeting at the planetarium, not here. So don't come here. The room will be lonely and you'll go, oh, I shouldn't be here. You should be at the planetarium. It is a walk. I mean, reserve your 8 to 10 minutes for a walk down. One final question, which is, did I pick up this correctly, that the Milky Way had an active galactic nucleus for a few hours?
Oh, well, so it was more active than usually. It was not quite at the level of an active galactic nucleus. So this peak in the intensity was, I think, 100 times more than what we have seen before, but still nothing at the level of even the activity that we, nothing at the level of the activity that would have created the Fermi bubbles, nothing at the level of the activity that we know happened in the center of the galaxy hundreds of years ago, where we see kind of echoes of the activity of the black hole in ripples and bubbles that we see in the region. But this is the strongest we have seen, not the strongest that the black hole is capable of. Ours. Definitely not an active galactic nucleus.
Right, Peter, yeah.
So was it just good luck that you found it? Because if it's just 2-3 hours, it's so hard to miss, right?
Yeah. We were lucky. We were lucky to see this spike, but there are a lot of campaigns observing the black hole activity and monitoring it. Spitzer has done that for a long time. There are many campaigns with JWST and with Keck. So it's people always try to match multiple instruments in order to trace these peaks in the X-rays as well. So we have seen peaks in the past, and people have been monitoring the activity of the black hole on and off. But of course, it's you do have to be lucky to catch a flare, but they do happen quite often. Nothing of that kind we have seen before, though. That's the bottom line.
All right, such amazing work over the years, and your own contributions seem equally amazing. So congratulations and thank you for this talk, and it's so nice to meet you. Let's like again.
Thank you all.